Okay. All right. Now, the first three questions, just to recap, were really to get you to understand that there was an acceleration, that a graph that looked like this, position, time, curved upward, since the slope was the speed would have been increasing and therefore it was accelerating. Okay. Now this is interesting. Can you guys hear me?
Yeah, we can hear you.
Okay. I think maybe it's just Gabby froze because I got you frozen.
Yeah, it looks like she's the only one frozen.
Yeah. Okay. I thought it was mine. Hey, my camera didn't freeze at all this last time. I updated my BIOS system over the week, so maybe that was kind of the issue. I don't know.
Awesome.
Oh, wait, I better knock on wood now. Now that I said it, my camera's going to freeze. I know it. All right. Well, I think she's going to pop right back in here. Hopefully, we'll see where she comes. Maybe I'll kind of look at the chat room in the meantime here. Let's see, you guys. All right. Now let me know if you see her come on in here. But let's see. Anybody here from 121? Doesn't look like it. I don't see any questions up there. So we'll see if she comes here. I'm going to save this piece of paper for when she returns. And we got another connection coming in. That's not her. Okay. Now she might be having other technical issues. Maybe she had to reboot her whole computer. All right, but maybe just at the risk of, I'll just play this out. Hunter, you were next on the list before a break, so let me just put here then chapter 18. If there's no 102 or 121 people, let's go to chapter 18, number 27. And I'll keep my eye out for her coming back. Meanwhile, then, I'll go 123, chapter 18, number 27, and I'll just put 1235 here and say, all right, let's look at this one. Okay. So we'll have to go away from my screen. So, guys, let me know if she comes back. 18, number 27. Oh, yes. Oh, how do you say these things? These are fun.
Yeah, I couldn't even pronounce that myself.
Yeah, there's stage waves, or I'm sure I'm not saying it quite right. Stage or something like that. But anyways, but basically what happens is during an earthquake. So it says, and an earthquake can produce a stage in a lake, which basically is the water kind of sloshing back and forth from one end. And so basically we have waves here, and they're going back and forth. So hopefully kind of the first thing that goes on in your mind is we have standing waves. Now the edges of it then can be treated as antinodes. Okay. So if I were to draw a standing wave pattern, and I think the easiest standing wave pattern for people to see, and that's why all the books and when I lecture, I always do the ones that have nodes at the end because they're, tied down. But there are other scenarios where the edge is free to move. And so the edges would look more like this. The edge would be here, where there's an antinode. And in this case, it is like that. In fact, it's so small, it's kind of hard to see. Maybe I'll redraw it. So if I had like, here's the level water, and it goes up and then down. And so here's the one end of a, say, a bathtub or a lake or a bay. And here's the other end. It would kind of be here at one moment, then this side would slosh up and this side would slosh down. And so the edges of the bay or the bathtub or whatever this is, I think this is a pond or what, a lake. It says a lake in which the water sloshes back and forth from end to end, which remains with a large amplitude any long period. Consider a stage produced in a rectangular farm pond as shown in this cross-sectional view. So suppose the pond is, okay, 9.15 meters long and a uniform depth. You measure a pulse produced at one end, reaches the other end in a time of 2.5 seconds. What is the wave speed? Okay, so the first part of this really is just saying that, you have a crest here, and then it ends up over there. That is, it traveled a distance of 9.15 meters and apparently took 2.5 seconds. Now, let me go back and read that 2.5 seconds. Was that just the time? You measure that a pulse produced at one end then reaches the other in 2.5 seconds. All right, so at this point, I would just say, this is physics 121. This is just the distance and divided by the time. So grabbing my calculator then, 9.15 is the length, and divided that by 2.5 seconds, I get a speed of 3.66 meters per second. So there's A, and really it didn't have much to do with waves yet. But then it goes on, it says, to produce this wave, people are going to make it. So they stand on the bank on one end and paddle together with snow shovels, moving them in simple harmonic motion. What would be the frequency of this motion? So here is where the wave part of this problem comes into play. The frequency would be the velocity divided by the wavelength. And we just did the velocity, so that's 3.66 meters per second. The reason this one is even in this chapter here on this one is right here, the wavelength. And so this standing wave pattern actually is half a wavelength. I tried to draw it up here, but from an antinode to an antinode is a half wavelength. Just like a node to a node is a half wavelength. Although, again, I think a node to node is easier to see, so we start there. But also, antinode to antinode is a half wavelength. So if I say then that the length of the pond is the 9.15, and that's half a wavelength, that tells me then that the wavelength is 9.15 times 2, and I get 18.3. So the wavelength would be 18.3 meters. And so then I can do 3.66 divided by 18.3 and come up with a frequency of 0.2 hertz. When our frequency that gets that small, I know this wasn't part of the problem, we like to do the period. And so the reciprocal is 5 seconds. So if you really wanted to make these with snow shovels or something pushing on the surface, you would go, every 5 seconds. So 1, 1002, 1003, 1004, 1005, 1001, 1002, 1003, 1004, 1005. And if you can get that rhythm right, the wave builds up bigger and bigger. And it's kind of a fun little game. I've never lived on a ranch or a farm and done it with a pond, but we used to do that in the swimming pools. You get the little floaty and put somebody on one side, and all you do is you just follow the pattern of the waves themselves. They're kind of natural. And anyways, and so the waves just get rocking in the pool. And in a bay, the same thing. That's kind of the dangerous about an earthquake in a bay. And then the water spills over the side and does all its damage.
Yeah, yeah. The hardest part I had with this problem was, I think, the visualization for me.
Ah.
Yeah. Thank you.
Yeah, you bet. Let me just check.
What formula did you use to find the wavelength?
If I did that right. Oh, good. I got the right numbers. What formula for the wavelength? Well, it wasn't so much a formula, although I could find one in the book. It was more of a visual picture. And so let me just kind of come back to a standing wave pattern. And again, kind of just natural to draw the ends at nodes, but they don't have to be. And so in this case, it was from an antinode to the next antinode. So if I kind of do this, okay, so.
Oh, I see.
Yeah, that'd be an antinode. And then to the next antinode would be there. And so
Okay.
lock this, how far is it from here to here? Well, that's a half wavelength.
Okay, that makes sense. Cool, thank you.
Good. And so all I did was say, yeah, L equals a half wavelength. So there's the formula. In general, it could be any integer number of half wavelengths. It would be 1 half wavelength, 2 half wavelengths, 3 half wavelengths, 4 half wavelengths.
I am back. I'm sorry that my internet went down.
Completely understandable. Completely understandable. Okay, now.
I thought it was you. I thought it was you because the computer got frozen and you began frozen. So I said, oh, his internet is down, but it wasn't good.
Well, I don't blame you. Mine does freeze a lot, but it wasn't this time.
Yes.
Okay. All right. So let's go to your question. See, 1244. Okay. So I was starting with you. Let's see. And here's a piece of paper I had. So I'm going to come back to it. All right. And so what I was beginning to say is kind of recap the first 6 questions. The first 3 were this. They were focusing on this graph. And here's what you were supposed to get at it. The first one was to say it was curved upward.
Yes.
The second part was to recognize that the slope is the speed.
Okay, yes.
And the final question, or the final of the first 3, I guess I should say, is that the slope was increasing. Therefore, that was proof that there was an acceleration.
Yes.
Okay. So that was questions 1 through 3. Now, questions 4, 5, and 6 were looking at a graph that had velocity versus time, and it was a straight line.
Yes.
And so you were supposed to say in question 4 that it was a straight line.
Yes.
5, you were supposed to say that the slope would then be the acceleration. And then the big thing, question 6 then, is this would tell you, because a straight line would tell you it has a constant slope, which is a constant acceleration.
Yes.
Okay, so now let's move to where we left off, number 7.
Yes.
Number 7 says, go ahead and measure the slope, right?
Yes.
Okay, so I'm going to put here slope, which again is the rise over the run.
Correct.
And the rise would be the change in the velocity, because that's what we're plotting on the vertical axis. And the run would be the change of time. And if I remember the data right, the last data point had a speed of 429.
Correct. Yeah, I have it here. Hold on a second.
Okay.
It is, yeah, 429, and the speed,
And what was the beginning speed? Like
the beginning is
45?
speed of the that's, we're talking about the velocity, correct?
Yeah.
It was, it was 45.
Okay, good. All right. So this is 45. So it had 45 at 1/30th of a second.
Uh-huh.
And then it had 429 at 3/30th of a second.
Yes.
Okay. So the slope would be the rise, which would be 429 minus 45.
Uh-huh.
And then the time would be 13/30 minus 1/30.
Okay. Yeah, that's how I have it so far too.
Okay, good. So if I go 429, 429, and I subtract 45, I get 384 in the top. And the bottom would be 13/30 minus 1/30. And so that'd be 0.4. So let me go 384 divided by 0.4. And I get a slope of 960. And the units are centimeters per second squared. So I guess we could just leave that alone right now, but number 8 is going to add to it.
Yes.
And say, okay, is this a good answer? Does this
No.
make sense?
I think it doesn't make sense.
Well, I'm hoping you'll say, yes, this is a good answer. I'm hoping you'll say, yes, this makes sense. Because what did this slope give us? Well, let's go back to question 6. Remember, question 6 tells us the slope is the acceleration.
Uh-huh.
So this is saying from our measurement of our lab, we got a slope or an acceleration of 960. Now, in my video lectures and in the textbook, I've been telling you the acceleration is 9.8 meters per second squared. Does that sound familiar?
Oh, yes. So, oh, yes. So it's close.
And that would be right. That'd be 980 centimeters per second
I
squared.
forgot about that. Yes.
Okay, good. Yeah. So
Because
I would say, yes, we did a good job. We got pretty close.
Yes, I see. Yeah, because it's close to that
Yeah.
number. Yes.
Yeah. So
I forgot about that. Not 80. I usually use the 10, or
Okay. Yeah, and I rightfully so. I use the 10 a lot also. But the 10 is just a convenience of calculation. But if you're actually
Yes.
going to measure something, you want to use the 9.8.
All right. Okay, that sounds good. Thank you.
All right. Well, now, hey, one more, though. Let me get you to the
Yes.
last one. Okay, so the last question, number 9.
Uh-huh.
You are asked to look at the graph that asks you to plot distance versus the square of the time.
Correct.
And it should look like a straight line too.
Yes, that looks a little bit messy though. At the beginning, it's kind of one over another.
Yeah, at the beginning they're real close together, right?
But they go get
Then
bigger.
they separate out,
Yes.
and that's okay. But question number 9 has 2 parts. The first part says, "What is the shape?" All right, so you could just say, "Well, it's linear."
Okay. Yes.
And then it says something like interpret or what does it mean? And to answer that, I'm going to take you back to your math class.
Uh-huh.
if I had a line on an XY axis, maybe you remember this equation, y equals mx plus b.
Yes, I do.
Okay, now b is the intercept. So in our case, our intercept is pretty close to 0.
Okay.
So I'm going to scratch this out. We have no intercept.
Yeah.
And in our case, our y-axis is the distance, and the x-axis is time squared.
Correct.
So I think the author could have gone further, but I think he gave you 9 questions and decided that was enough work. Because this is where you can stop. This is just saying distance is proportional to time squared.
Okay.
And you can stop there, but I do want to point out that in class we had this equation. And see, we're kind of confirming this equation
Okay.
with our measurements.
In that area? No.
Oh, no, A is acceleration.
Okay, excellent. Okay.
Yeah.
So let me write that. Is D equals 1/2
So D, yeah, this is distance.
at times square. Okay, I got it. Yes.
Yeah, 1/2
Acceleration. Okay.
and then time squared. Now, like I said, you don't have to go this far because like I said, if this was question 10 or 11, he could ask you a lot more, but I think he finally just decided, look, you've done a lot already. This is a good stopping point. Let's call it good for now. And so he just wants you to say something like distance is proportional to the square of the time.
All right. That sounds good to me. So I think I'm done for the whole thing because I already did the graphs, and I did the calculations and everything. So
Good, good. And now, so your next step is to put that into a PDF if you can.
yeah,
Okay. And
I
then
can do that. Yes, I can do that. Yes.
and then turn it in Canvas. You know how to do that too?
Yes, I know how to do that. Yeah. Okay.
Good.
So thank you so much. So maybe see you next week, or I don't know, be in touch by email. Okay.
Yep. And come by any Friday, and then also, shoot me a question by email anytime, like you've been. Keep it up.
Yeah, I usually don't have much problem with the math issues. I usually have problem with this writing.
Okay.
All right.
All right.
Thank you,
Well, that
Professor.
might.
Okay.
No,
bye-bye.
every week we have a few questions. So.
Yes.
Yeah. And by the way, this first one had 9 questions. We never have 9. We usually have like 3 or 4 questions.
All right. Okay. Okay. Bye. See you. Thank you.
All right. Bye now. Okay, here, guys. All right. So let me put that one down. And let's see, what did we got just done here with 18, number 27. I see here in the chat after. Oh, Daniel, these are both your questions. Should who asked from the morning about me doing one from the practice?
Me.
Chase? Okay. All right. All right. So I'm gonna follow that order if that'd be okay with you, Daniel. That I'm gonna go back to this.
Yeah, that's what the second question is saying. Do the list you had before.
Oh, okay.
And then.
Okay. So let me put down a time here. So okay. So 12:15. 57. And from 123, we'll do number 1 from the practice. Okay, good. And if I remember these practice ones right, the solutions gave 2 different methods on them. So let's see if I can find those practice problems. Let's see, they'd be on the solution page. Okay, here they are. Here's number 1. Okay, so number 1, page 1, this one looks like it might be kind of long. Looks like it's out of chapter 15. It's got a little spring here. It says a spring with a force constant of K fixed at one end. So the picture looks kind of like this, got a nice solid wall. And then the spring extends out. And instead of an object sliding back and forth, it's like we have an object that rolls back and forth. And I'm sure you remember from Physics 121, objects that translate and rotate are a little harder. You got to include Newton's second law for translation and Newton's second law for rotation. So I'm gonna split my paper down the middle and maybe put over here. Okay, I'll put some formulas for translation, and I'll put some formulas for rotation. All right, but I need to read it again here. It says a spring with a force constant of K fixed at one end is connected to a frictionless axle on a cylinder of mass capital M and radius capital R. The cylinder rolls without slipping. If set oscillating, what is the period? Now, maybe on the bottom of my paper here, I just want to remind you, I think you guys got this. I said it many times in chapter 15, that if you ever come across something that looks like this, a mathematical equation that says the second derivative of position or of something, doesn't have to be position, but it has a negative, then it has a something, and then that function back, then the solution to that is this sinusoidal motion, where this thing in here, if we call it box, would be the square root of box time and then some phase. And we typically called this thing omega, since it has that nice little mathematical pattern. So this would be referred to as omega squared. Okay. And then, of course, the period would be 2 pi over omega. And in this case, we're asked for just that, the period. So what we really need is to find omega. And the way we find omega is we have an equation that looks like this. And we're going to get that by writing out the equations of motion. So let me write out the equations of motion for translation, which says the sum of the forces equal to ma. And then let me also write out, fix that, there we go. Let me also write out the equation for rotations. And no doubt these are the harder ones, the ones that you have less experience with, and they're just downright harder. Okay, so I'm gonna start with the translation, and I'm only gonna look at the x direction. And so in the back and forth direction, okay, if I do a free body diagram, maybe I'll put the free body diagram here. There's this force from the spring. And it's kind of hard to draw an arrowhead from a spring because the spring keeps changing with time. You know, sometimes it pushes left and it pushes right. But also what's touching it is friction. And it says it rolls without slipping. So this would be a static friction. Now, technically, but I'm not going to look at the vertical, there would be a gravitational force, mg, and a normal force pushing up. So maybe just to complete my free body diagram, the phrase I like to use is take the force of gravity, so that, and everything that's touching it. So the table's touching it, so that's the friction and the normal force, and then that's the spring force. So over here, though, I would write it this way, that the force from the spring is minus kx. And then I would have the force of friction. And now, again, sometimes this is a positive number and sometimes this is a negative number. But let me just write it as plus. That way, if the force is to the right, okay, it's positive, but it sometimes in different moments in time, it'll be to the left. And then that would have to equal the mass of the object. They said capital A, and then this would be its translational acceleration. Okay. Now, at the same time, let me keep in mind that it is rotating. Okay. So I need to add up the torques. And just to remind you from physics 121, torque is the R, the F, and the sine of the angle between R and F. Okay. Maybe I should have put that off to the side. I'm just kind of reminding myself of, okay, how do I calculate a torque? So when I go to add up all the torques that make this thing rotate, the vertical ones go right through the center of mass. And so I'm going to calculate the torque from the center of mass, if that'll be okay. So that's one thing you got to make a decision on at the beginning is calculate the torque relative to what point? What's the pivot point? So I'm gonna take the center of this rotating object and calculate the torque. And as you can hopefully see, the normal force goes right through the center. Now, I suppose you might say the normal force is acting right at the bottom of this. They call this a cylinder. Yeah, the bottom of the cylinder. So in this case, the R would be the radius. The force would be the normal force. But this is the big one. The angle then would be 180 degrees because R would go from the center down and the normal force would go straight up. And the sine of 180 degrees is 0. Sine of 180 degrees is 0. And maybe it goes without saying, but the normal force does not make this thing rotate. There's no torque from the normal force. There's also no torque from the gravitational force. See, the gravitational force, we could say, acts right at its center of mass, which is its center. So when you go to calculate the torque from the weight of it, you would put a 0 distance here. So you'd have 0 torque. So again, you would say, okay, the force of gravity does not make it rotate. What makes it rotate, and depending on how you're looking at it, but I'm looking at it as a rotation from its center, even the force from the spring, because the spring is pushing right at its axis. So the torque from the spring, that R would be 0. So I would get no torque from the spring. The only thing making it rotate then is the force of friction. So I'm going to just start with the magnitude of the torque. We'll talk about direction in a second. But the magnitude of the torque then would be how far away, the r, so that would be the radius of the cylinder. It would be the force, so there's the force of friction. And then it would be sine of 90 degrees, because the force of friction would be left, right, and the radius up, down, and there's 90 degrees between those two. So this would be the magnitude of the torque. Now, here's where I better talk about the sign of the torque. So let's see, if friction is a positive number, so let's say the friction is pushing to the right, that would have a tendency to make it go counterclockwise. Okay, so positive force results in positive torque. If the force of friction is negative, this way, then that makes it go clockwise. So a negative force makes a negative torque. So I can just write torque as R times F sub S. I don't need the sign of 90 degrees because that's 1. And I don't need to put a plus or minus because that is determined by the sign of the friction. So I'll say it again. When the friction is positive, it rotates it in a positive direction. At least if we stick to the conventional coordinates. Okay. And so that would equal to your I alpha. Now, we might then, from that, do something along these lines, that the force of friction then would be this I alpha over R. And then we can use that back over here. So if I've done this right, I would have this minus kx. And in place of the force of friction, I'm going to put I alpha R equals MA. Now, there was an important part here, again, going really back to Physics 121, that said it rolled without slipping. Okay? How did it phrase it? Yeah, rolled without slipping. So that's why I put static friction, but that's also why I'm going to do the next step. If you remember, there was a connection between a translational acceleration and an angular acceleration. Okay? So let's apply this equation to this scenario, but we've got two things we've got to notice. First of all, the R would be the radius of the cylinder. Okay, so that's not a big deal. That's, this motion here would be the R. But I think we also have a sign issue. Let me see. Because if this thing had a positive alpha, so a positive rotation this way, so it was rolling this way, that would make it go in this direction. And that's the negative direction. So in other words, the translational acceleration is opposite of the angular acceleration, the way we've set up our grid here. And so that's, looks a little funny. It looks like just out of nowhere I threw a minus sign in there. But I wanted to kind of make sure we kind of see where this minus sign is coming from. In fact, you make me kind of wonder on the solutions to this. Let's see. Oh, I see. So Don did it from the bottom in this first one. Then he did it by an energy. And maybe I'll go to the alternative method. Sideways. I hope I can see that. What the heck? Oh, yeah. I think we're on the same path. I mean, I can't really tell you. Okay, but I just wanted to point out where that negative is going to come from, and the R. But the R is a little more obvious. It's that negative that isn't quite so obvious. All right, let me jump to page 2 here. Okay, so if I take this equation that we got, let me fold this over. So if I take this equation up here, which is the minus kx, and then of course I have the plus I over capital R, and now I'm going to replace it with this alpha here. So this alpha, let's see, I guess I'm going to have a negative A over R for that alpha. And then that would equal my MA. Okay. Now, here's where I'll have to kind of jump back to Physics 121. It's actually chapter 10 in the Survey book. What is the moment of inertia of a cylinder? And it's 1/2 times its mass times its radius squared. So with that in mind, the two R's cancel out. And I'll put the A here, and we'll have a 1/2 MA equals MA. Now, if I then move this to the other side of the equation, I get an MA plus a 1/2 MA, which is 3/2 MA. And now I'm getting close to that formula I said. Let me just write the 3/2 M, but the acceleration can be written as the second derivative of position. And I'll just take page 1 again and show you. I'm looking for something like this. The second derivative of something equals, and the negative and all this other stuff would get me there. And so I think I'm almost there. I got the negative. I can bring the 2/3 over. I've got the K. I can bring the M over. So there's all that over to there. There's the X, and then there's the second derivative with respect to time. So now I have it in this form that I was looking for. That means if I ignore the negative and I ignore the X, that thing right there, the 2/3 K over M must be omega squared. So that means the omega must be the square roots of 2K over 3M. And so the period, which we said would be the 2 pi over the omega, would now be 2 pi, and it would be the square root of 3M over 2K. And, oh good, that's the answer they got. And I think my working is probably best described by that one on the PDF that's sideways there, the alternative method, because yeah, I put the force in there, and yeah, and then, worked out the math. Now, I think a real clever way is to do it in terms of energy and then take the derivative of the energy, and you get the second derivative equation a little bit faster. But I kind of like that energy method. But then also you could have done it, and the first solution has it by doing it around not the center of mass, but calculating the torque from the contact point. That might actually be a little easier too. Kind of a judgment call there. Anyways, I'll do the other ones if you want, but I hope that helps.
Yeah, it did. Thank you.
Could you go over one more time about the negative sign on the alpha earlier? I sort of didn't follow that little piece.
Yeah, okay. Now, what we call positive and negative, of course, is a human definition. And traditionally, and so the first part of this equation, I'm doing tradition. See, tradition, and I'll start with forces, we call to the right positive and the left negative. Okay. We also traditionally call a rotation that is counterclockwise positive and clockwise negative. And that's how I started. I wrote out this equation right here, calling all the forces to the right positive and all the forces to the left negative. And then I also did the torques right here. And I stuck to the tradition here. That is, if it rotates counterclockwise, it's a positive torque. And if it rotates clockwise, it's a negative torque. But then here's where, if I'm not careful, I can run into troubles. When this cylinder moves positive, it rotates clockwise, which is negative. So I need to be careful between my math for rotation and my math for translation, because a positive translation results in a negative rotation, or the other way around, a negative translation. So when it goes that way, that results in a positive rotation. So if I want to compare my rotation to my translation, the way I have my grid, I need a negative sign, because a positive rotation needs to have a negative translation. Or the other way around, I think you see it later on.
Yeah, I think I follow what you're talking about now.
Okay. Yeah, I guess, and it's here. So a positive rotation is a negative translation. So anyways, I guess what I'm saying, and if I noticed this ahead of time, I probably would have tried to avoid it and make sure that a positive rotation goes with a positive translation. That's the warning I always like to give the Physics 121 students is, hey, when you start setting up your axes, make sure the positive in this column go with the positive in that column. Otherwise, you have to throw a magical negative sign when you compare the two. And I didn't see it coming, and so I didn't do that. And so my positive rotation goes with a negative translation, or my positive translation goes with a negative rotation. So I got to throw in that magical negative, and that's not the best way to do it, but maybe to have you see me have to deal with it is probably better. And kind of struggle through that. Oh, I didn't see it ahead of time, and I got to be careful about my signs.
How would you have set it up to avoid that?
Back here under rotation, I would have gone away from the tradition. I would have said, why don't we call a rotation clockwise a positive rotation? So usually I like to label it this way, positive. And let's call the rotation this way a negative. And if I did that, then back here when I calculated the torque, there would have been a negative torque. And that was where my negative would have come. I wouldn't have had to mess with it here. Yeah.
Got it.
And so it to me, it looks kind of magical when you have, positives over here corresponding to negatives. Then you just throw a negative when you compare them to, and it looks kind of funny. So it's just always better to have positives go with positives and negatives go with negatives, and you never have this magical negative sign between them. Okay, nice one. Okay. All right, now I think that concludes the list from, this morning. Okay, nice. And let's go back to the chat here and see, is there anybody from 121 popping in? Anybody from 121 got a question? Throw it at me. Even 102, I'll do you guys kind of quickly. You guys are a little bit easier, but I think we can move on down here. All right, so let's see. So let's go all the way back to you, Daniel. I think you wanted chapter 17, number 25. Okay, and I'll put a time here. What time is it? 1:24. And this is from 1:23. All right, so let me put here chapter 17, number 25. Good. All right, so let's jump here to 17. Let's see. So that's chapter 18. Let's go back up to 17. Number 25 is bottom of the first page here. All right. So let me read it here. Number 25 says the power output of a certain public address speaker is 6 watts. Suppose it broadcasts equally in all directions. Okay. A. Within what distance from the speaker would the sound be painful to your ear? And then B, at what distance from the speaker would it be barely audible? You can barely hear it. All right, so there's a couple of neat things here. And I guess I would start off with the idea of the sound level. What we call the sound levels, measured in decibels, is the log of the intensity compared to the smallest intensity that a human can hear. Okay. And we're asked for the distance that you would be painful, if you will. You might need to go back to the reading. I don't know if you caught this, but there's a little chart on sound levels, and the 120 is really a lot of decibels, and it's considered painful above that. Of course, everybody has their own definition of what's painful. So I'll leave that to the individual to interpret, hey, that is painful, or no, that isn't painful. But that's what we get out of the reading. And so when they say painful to the ear, they're indirectly telling you 120 decibels. Okay. I'm trying to say, okay, at what distance is it 120 decibels? All right. Well, let me start by trying to solve this. I'll bring the 10 over here. So that's a 12. That's the log of the intensity. And the other half of this is the human ears. The reference is 10 to the minus 12, 1/1,000,000th of a watt per square meter. So it's not much energy. The human ear is actually very sensitive to small amounts of energy. So anyway, that's our reference point. And so that, I guess that's the other thing you need to know. And so kind of the, what is the smallest amount of intensity that a human ear can hear? That's our reference. And then what's painful, that's 120 decibels. So this alone doesn't finish it, but it allows us to get the intensity, because if I take the anti-log, I would get over here 10 to the 12th. And then here I'd get the intensity over 10 to the minus 12. Then when I cross multiply, I get an intensity of 1 watt per square meter. So 1 watt per square meter is considered the threshold of pain. This is the 120 decibels. So if the sound is that loud, that's when it hurts your ears. Okay. Now to finish this, remember that intensity is the power over the area. Okay. And so the power was given, the energy coming from these sound waves, as it says, this public address system here is 6 watts. Now, if it goes out equally, maybe I'll draw a little picture here, but if you had like this speaker here on a tower, and the sound waves go out equally in all directions, that energy is spread out on a sphere. Now, usually we have, directed sound waves, because there's no point in sending energy upward. If this is trying to address the public, they're all, standing on the ground here. So you don't want energy going up in your public address system. So you're probably better off in a real system to, build something that makes the sound a little more unidirectional instead of isentropic. But taking this as isentropic, the energy would be spread out over the surface of a sphere, and the surface area of a sphere is 4 pi r squared. And so now I can solve for r. So moving r over to here, I would have 6 over 4 pi, and then I take the square roots. Now I suppose I should check my units here. Technically, this is a 1 downstairs, 1 watt. So I would have in the numerator 6 watts, and in the denominator, I would have watts per square meter, and then they would all be under a square root. So the watts would cancel off. The square meter would flip to the top when we simplified our compound fraction. And when you then took the square root, you would get meters. Okay, so the units are going to work out great. We're going to get a distance in meters. So now I just need to grab my calculator here and go 6 divided by 4 divided by pi, and take the square roots. And so 0.691 meters from this public address system, which is pretty close. You're less than a meter away. So yeah, it's going to be painful there. You're really close. Okay. Now, the other half of this problem is, where could you just barely hear it? And of course, barely hear it would also imply there's no other sounds. So I'm not sure anybody's really going to hear it this far away, because there's always going to be other sounds that drown out the public address system. But I will do the same thing for B that I just did for A. They're really saying here that the intensity would be 10 to the minus 12 watts per square meter. This was our definition of what is just barely audible. We don't even need to go through this, although we could say 0 decibels and then solve it and come up with this intensity. But we already talked about that number. That number is the number that is just barely audible for the human ear. So they're basically saying, how far away do you got to go before your intensity drops down to 10 to the minus 12? And I'll just put it the same way. This would be power over area, and the power is the 6 watts, and the area is 4 pi r squared. So rearranging this would be r squared, would be the 6 over the 4 pi, and then divided by the intensity of 10 to the minus 12. Then take the square root, and you'll get your r. All right, so grabbing my calculator here, I'll go 6 divided by 4, divided by pi, and divide that by 10 to the, ooh, didn't want to do that. Let me try that again. 6 divided by 4, divided by pi, divided by 1 times 10 to the negative 12. And then take the square roots of all of that. Whoa. 1, 2, 3, 4, 5. So 6.91 times 10 to the 5 meters. Maybe I'll write that as 691 kilometers. And so, which is a huge distance, but like I said, you wouldn't really hear this public address system that far. There would be absorption and there would be other sounds, but that's kind of the idea, if you will. And actually, let me jump over to the solution. That seems really far. I'm a little bothered by that. Let me check the answer. 25. So the first one is close, good, got that number. And the other one, oh yeah, that's what they got too. Okay. So, yeah, there we go. All right, what was next in our...
I had a question just like
Yeah.
on what we would do, how that would be on an exam. Say that were an exam question.
Yeah.
Because logistically, sometimes, it's like hard to remember everything that we've been given in charts in the book and things like that. So should I take time in preparing for this exam to go back through all the chapters and be like, this is where every chart is? Or is that material that would be provided on the exam? Like the 120 decibels that we needed, that's the part of that problem that throws me off the most, because I don't remember that it's there.
Yeah, that's a tough one. That's not my style, so I probably wouldn't have said. I would have just said, what position would be 120 decibels, which is the threshold of pain, and wouldn't kind of expect you to go and know that. But I would say that some of these reference numbers are, part of the learning process. They want you to know certain basic ideas. But I don't think long-term is important. What's more important than at that point is to say that, we have kind of a standard definition. And if you forget that it's 120 decibels, go to that chart. So yeah, I guess to answer your question is, yeah, know that they mentioned it, I guess. And so if you ever came across this question, you wouldn't remember that it's 120 decibels, but you would remember that there's a chart that said what it was. And so you would flip over to chapter 17 and look at the chart. Yeah, I guess that's kind of what you were saying.
Yeah, totally. It's sometimes hard when I've noticed this for myself taking these exams. I've got my exam up on my computer screen, and it can make it hard to do the problems when you've also got to then find the tab where you've got, because the book's on the computer too, so it's not like the book's sitting here right next to you, it's this weird thing that you have to deal with in the online space.
Yeah. Okay. Oh, that's a hint to me. I'll keep that in mind, so maybe you're not jumping back and forth so much. But of course, all these involve, I guess the same thing is true about all these formulas. You can memorize them, which if this was a classroom setting, that's, what you would have to do because it's not open book. So like in this case, knowing the definition of intensity and knowing the equation for sound level, both of those in a face-to-face setting, I would have expected you to put to memory. And in this online, I'm hoping you still will put it to memory, but you can use your book there. So I guess the 120 decibel kind of follows the same thing. I guess I'm kind of saying, you're right. It's a pain to flip back and forth. And I guess I don't expect you to flip back and forth to look up this equation, but you can. And I don't expect you to flip back and forth to know this equation, but you can. And I guess I would put the 120 decibels in that same category.
Okay, cool.
I don't expect you to flip back and forth because it's something that you should have committed that to memory, but you can.
Right. Okay, cool.
Yeah.
That explains it for me. Thank you.
Yeah. So in this online setting, I would encourage you guys to, try to know these all without having to flip back and forth like a face-to-face setting, but at the same time, maybe even right before the exam, remember what's where,
Yeah.
and just big picture.
The equations are usually easy because you end up using them so much that they sort of get memorized anyways. But things like 120 decibels that I've used this one time on this one problem are a little harder to commit to memory. But
oh yeah, not now that we just talked about it for 2 minutes.
Yeah, no, that one's stuck.
Yeah, I ran into a similar issue on one of the first exams last semester. I think it was asking for a chart in the stairway, and I was using the OpenStax book, so I had to scramble to try and find a chart that I hadn't seen yet in the.
Oh yeah, I think I remember I gave a hint to say, hey, look.
It was like an integral.
Oh, it was an integral, yeah, because Appendix B. Oh, okay, good point. Because I know that I'll keep that in mind because I know a bunch of the trig identities that we do in chapter 18. They're all listed in Appendix B in the survey, and I bet there's an equivalent on the OpenStax. And so, if when I'm writing the test and that there's something like that, and I'm not going to just say see Appendix B. I'll do both. I'll say see Appendix B in survey or see Appendix, and I'll have to find it in the OpenStax. Yeah. Good point. All right, so back to, unless you guys have more questions here, to our Zoom. Although it does look like it might be break time, unless, let's see, who's asking this next one? Let's see, that was Daniel. We already did Hunter's other one. After Hunter review, okay, we did that one. Oh, it looks like there is another Hunter one here. And
I asked another one, but if Jake hasn't gone yet, I'm cool with just waiting. I'll be here next session too.
Okay. In fact, I'll even write that one down, Hunter. So you've got chapter 17, number 48. So we'll do that after our break. Jake, you going to be here after the break?
Yeah.
Okay. 1735. Why don't we start with those two after a little break and come on back.
Sounds good. See you then.
All right. So it's our 1:30 to, no, what time is it? No, wait, it's not time for a break. Wait, I'm crazy. Oh, let's keep going. Yeah. I'm sorry. I looked at I don't know how I got that. Our break doesn't start till 2. All right. So let's do this one. 1735, although it's getting warm in my room. Let me change my switch. All right. Okay, so chapter 17, number 35, page 1. Yeah, we'll go ahead and do Jake's, if that's still okay with you, Hunter. And then
Yeah, no problem. I don't
and then
see
let me-
35 on here.
I think it's 37.
I think
Oh, okay, cool.
37?
Yeah, because there is no 35 in chapter 17. There's 34 and then 37.
Oh, you know what? Sorry, I meant chapter 18.
Chapter 18.
Yeah,
Okay.
sorry about that.
Okay. So I'm going to write this down. Chapter 18, number 35 at 142. This is from 123. All right. I'll put that in the notes. Okay, good. Let's find this one. All right. Let me switch over to the questions.
Was- Kind of struggling with the concept of like the fundamental frequency and what that meant.
Okay, I'll say something about that. So, all right, and I'll start off by making it more general. If you had something, and the easy one is a string. Now, this problem says a pipe organ, so these are not going to be string waves, but nonetheless, I'm going to just kind of start here and say, if you just had a string, and I'll draw a couple of pictures that you tied from between two walls. So I tie it here, and this is where it would hang straight across if I didn't vibrate it. And let me draw maybe 4 options. But the thing to recognize is that you will always have the endpoints as nodes because they are tied. They can't move. And that's what a node is. So our pattern has to look like this. The 2 ends have to be a node. So one option is it can look like this. Another option is it can look like this. Another option is it can look like this. Another option is it can look like this. And this keeps going on forever and ever and ever. Now, maybe to help you with the idea of fundamental, the longest wavelength, or put another way, the lowest frequency one. So this one here is the fundamental one. So if you ever hear anything say the fundamental, they are talking about the lowest frequency one, or the longest wavelength. Okay. Sometimes we also call that the first harmonic, because this one then becomes the second harmonic. Second. Then this one becomes the third, and this one becomes the fourth, and this one becomes the fifth, and so on. So there's an infinite number of them. And I'm hopefully by drawing 4 of them, you kind of get the pattern and recognize that this would just keep going forever and ever. Okay. Now, there are other options where the endpoint does not have to be a node. The problem before this, with the waves in that pond, the stages, however you pronounce those things, they are the endpoints are antinodes. And so sound tubes are like that. So if I made a sound tube, if the sound tube is open, it would be an antinode. The other end may be opened, or the other end may be closed. So if it's closed, this stops the molecules from moving. So this end has to be a node and this end has to be an antinode. If they're both open, then this has to be an antinode on both sides. And this discussion about sound tubes is what's appropriate for this problem. See, this problem, and so let me read it here. It says two adjacent natural frequencies of a pipe organ. So there it is. You're making sound with something that's a pipe, like a flute or a clarinet. In this case, it's just a pipe. Are determined to be 550 and 650. Calculate the fundamental frequency. All right. Now, let me do this. Since they don't say how this pipe organ is built, they don't say if it's a closed pipe organ or an open. I don't know if it's this one or this one. However, and mostly because I've done this before, I can see a pattern in those numbers of 550 and 650 that's going to make me eventually conclude that it's a closed pipe. Okay, and I don't expect you to see it yet. So let's talk about both options. I'll do the easier one first. The open pipe organ is easier than the closed one. So let's talk about that one. All right, so let me kind of draw a picture of a standing wave pattern. So if I just kind of went do 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 across my paper, and then I say, okay, so one end has to be an antinode, and the other one has to be an antinode. And so, kind of like I was trying to do back here with the string, there's multiple options. What are the options I can have where both sides are nodes? Now I'm asking, what are the options I can have where both sides are antinodes? And I guess I would see something that looked like this. If I cover it up here, maybe there's an antinode and there's an antinode. So that could be it. But also, I guess that could be it. There's antinode to antinode. Well, I guess this could be it too. This is antinode to antinode. I guess this could work too. Antinode to antinode. Oh, wait, this would work. Antinode to antinode. So again, there is an infinite number of possibilities that could occur. And if I were to draw them, kind of like I was trying to draw it for the string, and I did the string first, because again, I think the string is so much easier to see, because the node to nodes are just easier to draw and strings are easier to see in your mind. But let me draw the fundamental one. So
antinodes just the highest peak of the amplitude and the lowest trough of the amplitude?
yeah.
Okay.
Yeah. All right. So what I would call option number one, and I'd even call this the fundamental, if that helps you with your understanding of what is the fundamental one, I would say this edge is an antinode. It comes to a node and ends at another antinode. So the two ends are antinode. It kind of looks like this picture I was drawing first, where if I put the edge of my paper right here at an antinode, and I go to the next antinode. So that's kind of hard to see because it is only a half a wavelength. And because you don't see a whole wavelength, sometimes it doesn't look like a wave. But another option I was trying to point out would be from this antinode all the way to this antinode. So this would be an antinode on this end. Looks like there would be an antinode in the middle, and the far end would be an antinode. And so it would go like this. So that'd be option number two. And again, maybe I should put here fundamental. Let's see what other option I can have. So maybe I could start here at this one, have an antinode, and then end at an antinode. The only requirement is I have to start and end at an antinode. Okay, so this is an antinode. This is an antinode. Looks like there would be an antinode about there and another antinode about there. And so the wave pattern would look like that. I'll call that option 3. And let me draw one more. And hopefully, again, that's enough for you to see the pattern. And we can write out some equations and see the pattern. But again, I'll just say it just like it was for the string. But again, I think the string is easier to see. This goes on forever. There's an infinite number of these. And in this case, I'm going to start this end at an antinode and maybe finish at that antinode. Again, the only requirement is you start at an antinode and you finish at an antinode. Start at an antinode and finish at an antinode. In this case, there's an antinode in the middle, and halfway between that, there's an antinode and an antinode. And so the wave pattern, if I were to draw it, would look like that. Now, if we were to call this L, the length of it, so this would be the length of the pipe organ, I'm hoping you can see the mathematics here. This first one right here, I would say L is equal to a half wavelength. That's the hardest one, I think, to see. From an antinode to the first antinode is only half a wavelength. You got to go another antinode to get a full wavelength. And that's what this one is, a full wavelength. But I'm going to write it like this. L is equal to 2 half wavelengths. Because you can see the pattern better when you begin to realize the next antinode is just a half a wavelength further. And so the patterns that are possible, and I'll say it again, patterns, plural, and an infinite number of them, is to say that L can be an integer number of half wavelengths, where n is a 1 or a 2 or a 3 or a 4. So that's the 4 I've drawn. But I could keep drawing them, a 5, a 6, a 7, ... So this type of pipe organ, now remember, I'm talking about an open pipe organ. And I will give you a little heads up. I'm about to prove to you that the numbers they gave us do not work for an open pipe organ, but they work perfectly for a closed pipe organ. So this is a closed pipe organ, but I have yet to prove that to you. All right, so I'm starting with the easier one. So this is the open pipe organ. So the open pipe organ, if I said, well, what's the frequencies that are possible? Now remember, velocity divided by wavelength. So since these are sound waves in here, this would be that famous 343 or 344, whatever number you want to use. And the wavelength is why I went through this math here. Let me rearrange it. I'll put the 2 and the L over there and divide by n and set that equal to the wavelength. So I can write this as a 2L over n. So this would be 343 over 2L times n. Now, here is my proof, if you will, that the numbers they gave us would not work for an open pipe organ. Because if you look at this, remembering that n is 1 or a 2 or a 3 or a 4 or a 5, ... Whatever this first number is, it would be multiplied by a 1, then a 2, then a 3, then a 4, then a 5. Okay? So when you go from 1 to the next, this is the increase. Let's come back to the question. Did you read that? The question says, 2 adjacent natural frequencies. So they mean from this one to this one, or this one to this one, or this one to this one. But 2 adjacent ones are determined to be at 550 and 650. That's 100 apart. So what that tells me is they just told me that this number would have to be 100. And so I would have 100 times n. And so that means I would get patterns like this: 100, 200, 300, 400, 500, 600, 700, 800, 900. I'll stop there, but that does not fit their number at all. That does not work. Okay. So that should tell me that this pipe organ is not an open pipe organ. And since there's only two options, it must be this one. But let me prove to you that the numbers they gave us actually work really, really well. Okay. So let's see what we have. So let's do another discussion. And I should say probably a harder discussion. I'll say it again. I hope this string one is still making sense to you somewhat, because this is the easy one to see. It's from node to node. The little harder one, the one I just did, is antinode to antinode. Those are a little harder. But the hardest one is when we have a pattern that on one end has to be a node because it's closed, and the other end has to be an antinode. So let's study that one. And you're going to see when we study this one, the numbers they gave us is a perfect match. So this is going to be our proof that this pipe organ is a closed pipe organ. And then it's also going to give us the ability to answer the question, which is, what is the fundamental frequency? Okay, so to the hard one. All right, let me try to do what I was doing over here. Let me just draw a standing wave. Let me just have it fill up the whole page. Let me point out that on the left-hand side, it needs to be a node. Okay. So why don't I pick that spot right there? There's a node. And the other end has to be an antinode. So that could be here, 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 could be here. And so that's how we're going to get this infinite number again. All right. So maybe I'll just draw the first four again. I think that's the best way to kind of see the pattern, is to draw four of them. And so if you remember drawing this one a moment ago, we went from antinode to antinode. But now, dot, 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 this would be the fundamental one. The left-hand side would be a node. And this side would have to be an antinode. So from node to first antinode looks just like this. It's actually only a quarter of a wave. To me, it's such a small piece of a wave that it's difficult to see it. So why don't I go and draw some of the other ones, and you can maybe see it a little better. Again, remember what the conditions are. The conditions are that the left-hand side has to be a node and the other side has to be an antinode. So the first one I drew was supposed to represent from node to antinode. So the next one I'm going to draw would be from node to that antinode. Okay, so I guess it would look something like this. There would be an antinode, a node, and then on the far side would be another antinode. It would represent this. And that isn't quite a whole wavelength either. So this one too might be kind of hard to see, but it's getting close to a whole wavelength. So maybe that one's, I think, a little easier to see. Oh, let me go to the third one. Okay. Dot, 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 dot. And remember, the left-hand side has to be a node, and the right-hand side has to be an antinode. And so I guess I'm really going from a node to the next antinode. Actually, I just realized the pictures I'm drawing down here go up, and the pictures here go down. I hope that's not confusing. Maybe I should have done this. Maybe I should have put my reference node there. So the first one would have been from the node to the first antinode. This next one would have been from that same node to the second antinode. So there's one actually inside the tube. And the one I'm trying to draw now is from the node to this next antinode. So it would go up to an antinode, down to another antinode, and then to the next antinode. Now you can see that is a whole wavelength and a little more. And so maybe this is a little bit easier to see this one in here, that it's a wave. Because I got more than one wavelength in here. But again, I think this is the hard one because the conditions are node on one side, I'll put an N, and antinode on the other. Those are the tougher one to see. Now, I'll just kind of review. I drew the string one first because node to node are easier to see. The second one I did was drawing from antinode to antinode. And we saw that the pattern we got didn't match the numbers we were given. So that's obviously not the type of pipe organ we have. And I haven't proven it to you yet, but this pattern is going to exactly match on the numbers on our problem. So we're going to be able to prove that it's a closed pipe organ, and we're going to prove what the fundamental frequency is. Well, as I said, I hope I'm not taking too long. Let me draw the fourth one, and I think that'll give us enough to see the mathematical pattern here. But I'll draw from the node, okay? And let's see, this antinode was the third one I drew, so now I'm going to draw this one here. So it would be an antinode there. So it looks like there would be an antinode, another antinode, another antinode, and finish at an antinode. And so it looks like this is one whole wavelength and almost two. So, like I said, I think these patterns where you get at least a whole wavelength are easier to see that there's waves in here. These first two have less than a full wave inside of the tube, but they still are waves. They're just a fraction of a wave. Okay, but let's do this. Let's do like we did before. Let's say L is the length of the tube. Okay. Well, let me do like I did before in the margin. L would be what? This is the hard one to see. From this node to this antinode, from node to antinode, how much is that?
Quarter of a wavelength.
Yeah, good. So that's a quarter of a wavelength. Let's go to the next one.
3/4.
Ah, good. 3/4 of a wavelength. Oh, let's go to the next one. L equals. Well, do you see a whole wavelength and then another quarter?
Yeah, 1
5/4 of a wavelength.
So let me call it 5/4 so you can see the math pattern better. And then how about this one here, the last one? One whole wavelength. I'll call that 4/4.
7.
Yeah, 7/4. So as a summary, I'll go back to the open one. The open one was, I think, easier to see. It was just an integer number of a halves. What's this one? L equals, well, instead of having half, we have a quarter. And instead of having every integer, see how we have the odd integers?
So is it
1, 3, 5, 7. The next one would be 9. The next one would be 11. The next one would be 13. So I'm going to write it this way, M, where M is the odd integers. 1, 3, 5, 7, 9, dot, 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 dot. But let me play the same game. That is, like we did for the open pipe organ, let me put here, frequency equals velocity over the wavelength. Since these are sound waves in air, their velocity will be about 343. For the wavelength, let me put this mathematical pattern that we discovered. Let me move the 4 to the other side. So this would be a 4L. And we would divide it by M, and that'd be the wavelength. So let me put that down here. This would be 4L over M. If I simplify it a little bit, this would be 343 over a 4L times an M. And again, let me emphasize, because this is the harder one, M is not every integer. It's the odd integers. All right. So notice that when it goes from one to another, to another, to another, to another, M increases by 2, right? So we go from like a 3 to a 5, or maybe a 7 to a 9, or maybe a 19 to a 21. Now let me come back to this problem. This problem is hopefully making it very clear that your increase, I'll read it again, 2 adjacent natural frequencies of the organ pipe are determined to be 550 and 650. Okay? So to go from one to another, I would have this number here. And to go from one to another, this would change by 2. And that has to equal to 100.
So your fundamental frequency is going to be 50.
Mm-hmm. And so that means when I divide by 2, this stuff here, this is the fundamental. When M is equal to 1, all that stuff right there must be equal to 50. So this pattern is saying that I would get a pattern that looked like this. I would get a pattern where the first one is 50. Then we would go up by 2 times 50. So we'd go up by 100. That'd be 150. And we would go up another 100. That'd be 250. We go up by another 100. That's 350. We go up another one. That's 450. Then we go to another one. That's 550. And we would go to another one. That's 650. And that's exactly the pattern that they gave us. They gave us an increase of 100 with a fundamental of half that at 50. And knowing that would be a sequence of odd integers is why, with experience, I knew, okay, this is going to be a closed pipe organ. Because the difference is 100. And if I counted down 100, 100, 100, 100, 100 evenly, which is what you get for an open pipe organ, it doesn't work. So I was like, okay, this is not an open pipe organ. It can't work. But if I go down 100, 100, 100, 100, 100, I get to 150 and then go 100 to 50, the original is half the difference. That is the sequence of odd numbers. Mm-hmm. And so that's how I knew it was going to come out to be a closed one. All right. So we, I think, answered A. At what frequency? No. two adjacent ones. Oh, calculate the fundamental frequency. So we did that. It's 50. And then also the length of it. So to finish this one, we are saying that the 343 over 4L is the fundamental frequency of 50. And therefore, L is... So this would be 343 divided by 4 divided by 50. And we are looking at 1.72 meters. And I better check the answer on this one. What is, I forget what number this was.
35.
35. Yeah, they got 1.7 meters. Good. And they got a fundamental frequency of 50. Ah, good. Nice.
Awesome. Thank you so much. That really helped me visualize it.
Good, good. Yeah. And I went to all the different patterns. Hopefully that will help you on other problems. But I fear when I do that, I may make this problem look harder than it really is. But in order to see the closed pipe organ, you really got to understand the string first. That's the easy one. Then you got to understand the antinode to antinode. Finally, you can then get to the harder one, which is a node to an antinode. And then fortunately, that's really all the patterns we have.
So if you were to like take a guitar and then compare the like high E versus the low E, the difference is just they're just increasing by a proportional frequency, I guess. Or
Let me be careful with that question, because on a guitar, the high E and the low E are different strings.
okay.
So, you know, we're not trying to say that there's a mathematical connection between them like back here. Back here, this is supposed to representing the same string. The same string can be doing this and this and this and this. Okay. Where you on a guitar are comparing a totally different string. That string has a different tension. That string has a different mass density. So the high and low E don't fit this pattern. That's not what I'm trying to say. Now, that's not to say there isn't a mathematical pattern, because music has mathematical patterns. And when you go up one octave, you double the frequency. So the high E does have twice the frequency of the low E.
Okay, but physically they're not.
But it's not because they're on the string like this, you know.
Okay.
Yeah.
Yeah. Thank you so much. That I can.
During that, I sort of I see the forest, but I sort of lost the tree that we were going for there.
Okay.
Can you just walk me through a little bit more of why we did what we did to get the fundamental frequency of 50?
Yeah. Well, let me start off by saying I went and I reviewed everything, okay? But here is what I think the intent of this problem was. If in the chapter, and of course I know you're still learning, but let's say you perfectly learned the chapter. You should have walked away from the chapter saying that if I have an open pipe, I will get patterns that follow something times 1, something times 2, something times 3, something times 4, something times 5. Okay? But if I have a closed pipe, I will get patterns that follow a 1, a 3, a 5, a 7, ... Okay. So if I take away all the reviewing I did, which was, you know, most of the time here, okay, I would just jump in and say, okay, given the numbers they gave me, what pattern fits here? Because the open one would be the fundamental times n. And the closed one, the frequencies would be the fundamental times m. Now, if you look at the patterns they gave you, 550 and the next one is 650. If you try to compare it to an open pipe, which go by every integer, you would continue to go down and you get to 450, you'd get to 350, you'd get to 250, you'd get to 150, you would get to 50, and then you would get to negative 50. There's no zero, right? It's not a multiple. This pattern does not fit the pattern of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay.
But it does fit this pattern. It does fit a pattern. And so I'll go 650, 550, because it does fit a pattern that would be a fundamental of 50 times 13. And then this is a 50 times an 11. And then this is a 50 times a 9. And eventually I would get all the way down to 50 times 1. And so I can take a fundamental times the odd integers and make it fit this pattern. I cannot take a fundamental and multiply it by an integer and make it fit this pattern. It just won't work. And so I felt like I needed to convince you of where these patterns came from. And that's why I took so long trying to draw. In fact, I went all the way back to the easy one to see, which had nothing to do with this problem because this is a string. But by looking at this pattern, maybe it makes it a little easier to see the open pipe. And the open pipe, I was trying to convince you and prove to you that it followed a pattern of 1, 2, 3, 4, 5, every integer. Whereas the closed pipe fits a pattern of the odd integers. And so I'll say it again, the idea of this problem really was that you came in knowing that open pipes follow this pattern and closed pipes follow this pattern. What do we have? And once you see that, this is actually a 30-second problem. I mean, when I read it, and I was just like, oh, yeah, clearly it's closed, and clearly the fundamental's 50.
Right. Okay.
How else could that pattern work?
The fundamental will just be the we'll take it all the way back to 1, and that's where we started. That's our fundamental, and it'll just increase by that amount every time. Okay.
Right.
Now, if this was an open tube, and let's say your frequencies were 500 and 600, would your fundamental frequency be 0 or?
Oh, it would be 100.
Okay.
So yeah, so if you had, what would you say, 400 and 500?
Yeah.
All right. So that one, I could count it down and say, okay, well, the next one is 300. Because this would essentially be 100 times 5. This one here would essentially be 100 times 4. This one here would be 100 times 3. So it is fitting the pattern. Let me go 200. It'll be 100 times 2. 100 times 1. And so the fundamental one is right there because this pattern starts at 1. Doesn't start at 0.
And this would be a case where.
Although I think this
so
pattern would actually fit here too, right? Couldn't this be also 50 times? No. Well, maybe it doesn't fit. Oh, good. Yeah, so. Yeah, it doesn't fit. Okay, good. So it doesn't follow this pattern. So yeah, so if I saw this pattern, if I just saw 400 and 500, I would know right here it's closed. I know it follows this pattern, and I know the fundamental is 100.
Would I be right in saying that if I've got an open pipe system, then my delta F, like the change in frequency, I can find the fundamental by just dividing that by 2, and then
The delta F and the fundamental are the same thing for an open one.
oh, sorry, yeah, that I meant for a closed pipe. For a closed pipe, I divide it by 2, and for
Yeah.
an open pipe, it's the change in frequency.
Right. And so you're seeing exactly this math, right? That's what this math means, right? The math means it increases by 2 every time, so the fundamental is half that much. And then the open one, the increase is just 1 step. And so the increase is the same as the fundamental.
Got it. Thank you.
Yep. And so it's more of experience. I admit it's experience knowing that we have 2 kinds of patterns, and patterns of even integers versus odd integers. I'm sorry, not even every integer versus odd integers. Yeah. And so once you know that, and then like I said, that's where this problem was in theory supposed to start. In theory, it was supposed to start by saying, the pattern of an open is every integer, whereas the pattern for a closed is the odd integers. Which one does this match? That's how this should have been tackled. And then it's like a 30-second problem. But and maybe I should have started there and then proved to you afterwards that these are the patterns. But,
well, I get it now. Thank you.
Good. Good. All right. Hey, that was a really good one. And our break time, or past it. Why don't we take a little break and stretch our legs for 35 minutes and come back at 3?
Thank you.
So much.
Uh-huh.